Today we need to discuss enthalpy, which is one of the prime topics in thermochemistry that we'll discuss. Enthalpy is just heat transfer that's carried out under constant pressure. Usually what we're talking about when we say this is the essentially constant pressure of Earth's atmosphere. Enthalpy is extensive, so that it depends on the amounts of reactants in the reaction. It's equal in magnitude but opposite in sign for a reverse process. So a reaction going in the forward direction may have, say, a negative enthalpy, for instance, whereas one going in the reverse direction would have the same magnitude but a positive value. And it depends on the states of the reactants and products, because energy is required to change those states. That's going to be important. Some examples are as follows. If I look at the reaction between hydrogen and oxygen to produce 2 moles of water, we can see that the energy change is about negative 483.6 kilojoules. If I take that down to make only 1 mole of oxygen, it should release half as much energy, and it does. Reversible, looking at that same reaction, producing the water releases the 484 kilojoules. Reverse the reaction to make oxygen and hydrogen from the water, and it requires me to supply 484 kilojoules. And then if I look at the reaction in the gas state, taking 2 gases and making a gas, it's the same reaction we've been looking at. However, if I make it produce liquid water, we can see we release far more energy, because the gaseous water has to cool down in order to become liquid water, and so it gives that energy off to its surroundings. Another handy tool we can use for enthalpy is Hess's law. And some things we need to remember about enthalpy to work with this is that enthalpy is a state function. If you don't remember, what that means to you is that the path we take to reach the end is immaterial. The only thing that matters is where I start and where I end. As a result, the sum of the enthalpy changes for any set of steps that lead me to a certain final state should equal the change in enthalpy for the same direct pathway between the initial and final states. Remember the example we had in class about driving from Bentonville to Denver, Colorado, how it didn't matter what path you took, your differences in elevation were still the same. You may drive different miles, but if we're just talking about your elevation from sea level, the difference from where you started and where you ended is the same. And so that leads us to the equation below that says that the enthalpy change for a reaction is just the sum of the steps if we carry this reaction out in a series of steps. If we do it all at once, that's the direct path, and it will equal each of these steps added together. So here, let's take an example problem. We want to determine the change in enthalpy for burning methane, in which liquid water is produced, given that the delta H of combustion, or the delta H of burning, is negative 802 kilojoules for the combustion of 1 mole of methane, where all species are in the gas state. And then we also know that the delta H of vaporization of water, or the energy required to convert water into steam, is 41 kilojoules per mole. So here is the first reaction that we have. Combustion means to combine totally with oxygen to produce CO2 and H2O. So we'll write that reaction out. Methane plus 2 moles of oxygen makes carbon dioxide plus 2 moles of water. And we're told above that the enthalpy change for this reaction is negative 802 kilojoules. This is very exothermic. You should be aware of that. You burn natural gas to make heat. But this is doing everything in the gas state. And that's the way combustions are written. So this is a problem. We want to know what happens when I produce liquid water. What Hess's law says is that I can make all this gas and then pretend like I do another step where I just condense the water. It would be the same thing in the long run as making the reaction happen where I produced water straight away. All I have to do is show how much energy needs to be lost to do this. So I take the delta H of vaporization of water, which I just told you is the energy required to turn water into steam, and I want to turn steam back to water. So I'm going to write that in the opposite direction, where I have 2H2O gas becoming 2H2O liquid, and we're going to make that 2 times that amount, because we're working for 2 moles in this equation. There are 2 moles of gas water vapor produced, so we want to convert 2 moles back to liquid. So we need to multiply the magnitude by 2 and change the sign to a negative since we reverse the reaction. And so the reaction that we actually have then is the one that we want. We're burning methane and oxygen to produce carbon dioxide gas and liquid water. And the delta H for that reaction that's shown in black is just the sum of the two individual steps. And so we do that at the bottom, the negative 802 for the burning, and then the negative 2 times 41 kilojoules for the condensation, and see that a total of negative 884 kilojoules is released in this process. Another example is shown above. It's a little more complicated, so we want to see this. They're asking me to use the two equations that they gave me, the information and the enthalpy changes, to determine the delta H for the reaction below. On the basis of that enthalpy change, is this a useful reaction for the synthesis of ammonia? Alright, so the first thing we want to do is to determine where my reactants are in the equations above. Which side are they on, or which reaction are they in? If I look closely, I can see that my nitrogen gas is located in the first reaction. In the first reaction, I am producing half a mole of nitrogen gas. That's all well and good, but for my reaction that I'm of interest that I'm looking for, I need to take 2 moles of nitrogen and react them, not produce, and definitely not produce half a mole. And so I need to take this reaction, flip it, so that nitrogen is now a reactant, and instead of a half I need 2, so that's a factor of 4. So I need to flip this, hence the negative sign, multiply by 4 to get my coefficients the same. We do the same thing for water. There are 6 waters involved in the reaction of interest. Reaction 2 up there has water in it, but it only has 3. It also has water as a product. I'm interested in water as a reactant. So again, we're going to take the reaction and flip it. So that's a negative sign. And then I'm going to multiply by 3 to make my coefficients the same. So these are the 2 reactions that I'm going to add together. And I've made the adjustments for their direction, the negative signs, and their magnitude, the numerical coefficients that we're multiplying by. And so if I add those together and cancel out like components on each side, I'll see that the hydrogens will cancel out such that I produce the equation of interest. 2N2 gas plus 6H2O gas makes 4 ammonia molecules plus 3 oxygen molecules. And so my delta H should be the sum of those 2 steps. So take negative 4 times 46 kilojoules and add it to negative 3 times negative 484 kilojoules, and see that this reaction requires 1,268 kilojoules of energy to happen. So would this be a useful reaction for the synthesis of ammonia? Probably not, unless you are willing to supply very large amounts of heat to make it happen. If that's cost effective, then maybe it is. But usually the lower energy a reaction requires, the more suitable it is for use in industry. The last little bit that we'll do with basic enthalpy and Hess's law is to use standard formation enthalpies. Essentially, what has happened is chemists have collected large amounts of data on certain reactions and reactants and decided then that if I form an element or a compound from its elements in their standard state, then we'll define that as the enthalpy that's required just to make that compound. As it turns out, all elements in their standard state are arbitrarily assigned a value of 0. Because they exist in nature, it takes no energy to produce them. And so they're all 0. So if I have, for example, hydrogen and oxygen reacting to make water, any energy generated from that must be due to the formation of water. If I've assigned hydrogen gas and oxygen gas formations of 0. And so that's the little game they play to calculate these things. And so we want to apply this in the context of the path that we're taking not mattering. If you remember back again, we said enthalpy is a state function. So I've just chosen to make my steps very special steps where everything is a pure element reacting to make a compound. And if that's the case, then I can use the data from the tables. So the standard state that they're talking about is 1 bar, or approximately 1 atmosphere, 298 Kelvin. This is essentially 25 degrees Celsius. And if they're solutions, the concentrations will be 1 molar. And so how does this work? Well, what we're saying then is that the delta H for reaction will be the sum of all the formations of the products minus the sum of the formations of all the reactants. Well, why do we do it in this order? Well, if we look at what's going on inside the system, the reactants are being formed, and so those are the bonds that are going to be reassembled. So any energy that's going to be in the end should come from that side. The reactants already have the energy, so we're going to look at what's available in the reactants, what happens with the products, and look at the difference. If that difference is a positive value, products require more energy than reactants, then it's an endothermic reaction. If the products require less energy than the reactants, it's exothermic, and we'll show that being released to the atmosphere. Alright, so this is our equation of interest. We're going to take 2 CO2 gas, react it with H2O liquid to make C2H2 gas and 5/2 oxygen. Here's my data table. I know that CO2 gas requires negative 393.5 kilojoules per mole. Releases that much when it's formed. Liquid water releases negative 285.8 kilojoules per mole, and C2H2 gas requires 226.7 kilojoules to form under standard conditions. We're going to notice right off the bat we have a pure element in its standard state. We have oxygen. The formation of oxygen is zero. No matter how much we're forming, it is zero. Or how much we are starting out with, it's zero, because it's in its standard state. So we're going to totally ignore it. So one of my products is already set to zero. Next, we'll take the remaining product. It has a coefficient of 1, so 1 mole times its formation, 226.7 kilojoules per mole. So that's how much energy is needed to create it. How much energy do I get from the reactants? How much is available in them as potential? Well, there are 2 moles of CO2, so I'm going to subtract negative 2 moles times the delta H of CO2. There's 1 mole of water, so negative 1 mole times the delta H of formation of liquid water. And then I just run this through and do the math and see that the delta H then for this reaction is about 1299 kilojoules. So this is a very endothermic reaction. The formation of this is not exothermic. And that will end our discussion of simple enthalpy.